I would say most of your like hydrology preparation, the pre-processing work will be done in GIS. So if your group is going uh, to perform these type of tasks, say if you're gonna, even if you're doing design, but this is one of the topic you're going to touch on. So so hydrology is the input of everything. So design work in hydrology because that's uh, what dictates how much inflow that's coming in. So even if your focus is on design work, but then who's gonna do the prep work, the pre-processing work for you, right? So you will still have to do it somehow, right? Uh, so if in the future your team is going that direction, then you'll be doing some uh, in-house design work, then I would suggest that you also invest part of your budget to make it to GIS, or maybe just get additional 2 3 license so the team can utilize. I think that's it will be very. I mean, we use GIS every day.
Yeah.
That's like
Yeah, that was Tesla project make a lot of sense because the area is huge, right?
Excel
You're talking
projects,
about a square mile,
Yeah.
not even acres, right?
yeah.
So those JS will be really handy, right? Engine way, good luck. So you might chasing, like top of the hill, I mean, it's a huge basin.
Yeah. Yes.
But yeah, we definitely can look into that. I mean,
Yeah.
we just need to budget it, right? But the thing is, you kind of need to know to use GIS to some degree, right?
Mhm.
Right.
Yeah.
That we have to set up to.
Yeah.
Like, for example, we have sentences to get training in GIS, right? Before you can incorporate into the hydrology part.
Yeah. No, we can also cover GIS.
Oh, really?
Yeah. Yeah.
Yeah.
Because we use GIS.
Yeah, because well, actually, the GIS is handled by we have a group of GIS groups in the county.
Special team.
Yeah, I mean, in the county, there's
Okay. So we.
they're like GIS group, right?
Mhm.
But the thing is, they don't really provide training, just handle all the GIS need for the county. They in charge of all the licensing for
Okay.
different department.
Yeah. Yeah.
Certainly, we can budget
Yeah.
in the future, maybe with license.
Well, yeah. Feel free to. Yeah. Let me certainly provide some suggestions. Uh, that will help your team, depending on your direction, or what will be needed. I can provide some suggestions. Yeah,
Very good. Well,
yeah, yeah. So guess we can get some
get started.
Yeah.
Okay.
Okay. So the focus today, the next 2 days will be just the hydrology part of the modeling world or analysis world. So typically, as the name H and H, right? You have hydrology and hydraulics. So the hydrology part is we know it's everything that's related to the flow, the production or the generation of flow. So from the precipitation uh, and how they get transformed into your flow, that's the hydrology part. And then the hydrology part will feed into your hydraulics part. So the hydraulics, uh, you can think of it as the physics of water. So once you have the flow, then you feed into the hydraulic part. Then based on that, then you can analyze the response, the physics of the flow that's within your system. Uh, could be your roadway, your subdivision, could be natural channel. So that's the second part. That's the hydraulic part. So today we are. For the next 2 days, we're just going to focus on the hydrology part because, and then, as you know, in school, hydrology it's its own particular class. So trying to condense everything,
Right.
try to cover as much we can in the next 2 days. So for today, and like I said before, um, we're just gonna keep it really, really relaxed. And then, feel free to ask any question or stop anytime you want. Then we don't need to rush it, just see how everybody feels and if any specific topic that comes up, then we can spend more time. So that would be the goal or the style that I think will be good for us.
So there's 2 days just for hydrology.
Just hydrology, yeah. So for today, this is like the tentative, agenda for today. So we're going to give a brief introduction, and then also talk about the objectives for today's material, and then we broke it down to 4 sessions. So we're gonna start from the basic hydrology concept, and then after that, then we're gonna revisit this rainfall to runoff transformation concept, how the rainfall is converted into runoff. Then the third session, so then we got before everybody's falling asleep. So session 3, we're gonna have a little, exercise. So we're gonna work together, and we're gonna create a basic HMS model. So that way we can visualize, we can actually see how rainfall is input into the model, and what's going to come out of the model. So that'll be session 3. And then session 4, if we have time, I do think we'll be able to cover that. So that will be session 4 will be more, I would say, practical, because we'll be developing or determining peak flows, and then for design purposes. So how we would convert the peak flow values if we need to run let's say a swing model or a steady model. How would we convert peak flow value into a time series linear hydrograph for the subsequent modeling purposes. Okay, and then tomorrow, day 2. So we're thinking to first that we're gonna cover, since you mentioned about, there could be also land development, site development projects, even though it's not within each group, but it'd be good to also go over what they do a little bit, and so that way we can understand, what your team is doing, what our team is doing. So there'll be some background information about land and site development, and how hydrology or detention, what roles does detention play in the site development projects. And then session 6, so 2 is going to be the hydrology EDU. So that will be also a hands-on exercise, hands-on session. And then the last one, depending on how we feel about it. So coming from consultant, so we typically we would before we submit everything, we go through the QC checklist. So what's including the QC checklist is that all the steps, all the key elements that that we should cover throughout your projects. So we go through the QC checklist at the end to make sure that we're not missing anything. So if you think about it, QC checklist is actually like a roadmap of your project. Because if you meet all the checklist, the items on your checklist. That means that you're carrying out the project in the right order, and then you include all the essential elements. So that's the plan for the next 2 days. Okay,
Yeah.
sound good?
Yeah.
Yeah.
And we can adjust too as we
Yeah, we can
as we
adjust.
see. So.
This is really because we don't know each other, that this is the first time we meet. So, but but from the feedback and the interaction, during the sessions, that we can certainly adjust. Okay,
It's a similar training you provide to tech stuff for the hydrology.
similar style. But like I said, every training that I conduct totally different. Material will be this hydrology is this only, everything is already developed, but depending on the audience, we will modify our style, so that way it's benefit to the group, you know.
Mm.
Okay, so just a little bit about myself. So I'm Ted. So I've been in the industry for the past 20 some years. So mostly in H&H, I did a lot of analysis work, and then also teaching is a big part. So I used uh, to teach at the University of Houston, open channel hydraulics for about 7 years. But I was also working full time as let's say consulting engineer. Yeah, so both academia and then consulting. Yeah, so I've been involved in both areas. So that's my background. So not only with the riverine system, urban drainage, and also coastal hydrodynamics, wave. It's also my it's also on my resume. So feel free to let me know, because I also learn a lot from every time I teach. So we're always learning. So, and I don't know everything. So it's good to also you learn from each other. Yeah. Teresa, you
Yeah.
like
And
to
I,
introduce yourself a little bit?
yeah. And I'm Teresa. I'm a 5-year EIT. Graduated from U of H, and I started off on the drainage design side, mixed with a little bit of H&H, and continued on the drainage design side. And I've kind of flipped back and forth throughout the past 5 years. So I've been able to learn a little bit of both, from the H&H softwares to the drainage design softwares, and different criteria. Um, and I've been at AGA now for 2 years. Um, and now I'm a part of more so the H&H side. So that's been that's been a learning curve for me. So but it's been very interesting, and kind of see how it compares from like a drainage impact standpoint versus like a drainage design standpoint. So but yeah.
Yeah, I think I would say, from what I'm seeing from Teresa, because she was a designer, and then for her, yeah, making the transition from design to analysis. Yeah, sometimes because the way that designer, they have different criteria in analysis, it has a different set of criteria, but there's some overlapping in between. So especially if you, let's say, if you are a pure designer, that you don't get confused. But you're a pure um, analyst, then you don't get confused. It's only when you do both, then your mind, you be thinking, okay, which set of criteria covers, right?
Yeah.
So that's sometimes it could be very confusing.
Yeah, I always think about it. I'm like, what lens am I looking at it through? I always have to check myself, remind myself. Um, uh, yeah.
How about we'll go around Chris or Evan? Would you like to share a little bit about yourself?
Yeah. So I'm in May, it'll be my fourth year of being an EIT. Graduated from CU Boulder from Colorado, and I worked for a design land development firm for 2 years and then started here. And yeah, I work in the design group. That so doing projects like one right now I have where we're replacing cross culverts and expanding the road and driveway expansion and other stuff. A little bit of background in hydrology. Got my degree in environmental engineering, so I have taken some hydrology classes, less hydraulics, but yeah, and a little bit of practice with that here as far as hydrology goes.
Actually, just say, well, we have some stable life project that we call it. So this is a big county, right? We still have a lot of county road. It doesn't have a payment structure. Basically, just one of the natural materials there, right? You know, back then, the farmer, the ranger, you know, going from point A to point B, they just plow the road, right, and access and become a county road, right? And the county don't even own the right of way. That's when I first come join here 15 years ago. I'm working for DOT, for Tesla and Caltrans in California. And come here like, you don't own right of way. Go, what's going on here, right? It's common. So we don't own fee title, right, to the right of way. But we just call basically it's a prescriptive right of way. I never heard that term in my life, right? It's a prescriptive right of way. So basically, just scripted county maintain the roadway. So the property line to the center of the road. So yes. So people on this side and that side paying taxes on this county road. I mean, it's a street, it's not very much, I mean, especially in the rural area, right? The taxes, I don't think the public tax that expensive, but either way, but so that's kind of eye-opening, right, for me. But so going back to stabilized projects we do. So it doesn't have a payment structure for us to rebuild a road. We can't. It's kind of expensive, right? People design it, you know, with a payment structure, all the drainage. And we have 100,000 a mile road like this, right? So if we don't do anything, it's gonna get worse and worse. It's the natural material. So we established a program called the Stabilize. You know, so what we do, we're using different method, right, as we go. So right now, we're using the Stabilize with a foam asphalt. So basically, we have TTI in College Station. There's a professor, or he's not professor, the researcher. I don't even know his name, Tom Scallion. So anyway, he's from like Scottish, right? He's a Scottish from Scotland. It's really good. So he would come up with design. So how we come up with design, we come up and get the material on the roadway, right? Ship to the lab and see what's there, right? So we come up with design usually 90%, because especially on the east side of the county, it's kind of unique, right? Williamson County here, I-35, run pretty much in the middle, give or take, right? So everything west of that, the further west you go, the soil gets better. Further east you go, it ain't worse. So on the east side, it's all like a black clay, right? So clay is not good material. Well, good for certain application, right? Certain things you need clay, right? Like you're being a dam, right? You need clay, right? Like roadway, not so much, right? Because expansion, contraction, right?
Drainage is not so good.
Right. So anyway, so we instead of rebuilding all the road, right, it's just impossible. We don't have the money, right, and the time. Right? You know, if you contract it out, it would be too expensive, right? So that's what we do a lot of work in-house. So we just pay the employee, right? Pay the equipment, you know, and buy the material. Pretty much it, right? You know, and we have the people can fix the equipment, you know. So it's really effective. If you would contract it out, we cannot have that much money, right? So on the stabilize project, basically we're going to just stabilize the roadway, you know, with TTI design recommendations. I say 90% of them, they need to put some clay, like lime, you know, to stabilize the clay on the subgrade, right? So above the subgrade, we use called the foam asphalt. It's a really cool piece of equipment. Is working. It's the name. It's a company name. The machine called the working machine. Right? It's a German. It's a German. Right? They come up with this machine. It's a refiner basically. Right?
Mhm.
But the cool thing is they would polarize the material.
Mhm.
They polarize the material into the drum. They shoot hot asphalt right inside the drum and water. You say oil and water is not mixed.
Mhm.
You're right. You know. So the way I look at it, it's kind of look like espresso when you go to Starbucks in the morning, right? Buy espresso, you know, it's just hot, you know, you inject some cold milk in there, right? It's just warming up. So that's what it's doing, right? With hot asphalt. So the machine you can hook up. We have a distributor come in with a delivered hot asphalt.
Mhm.
They put a hose and connect to this truck, and not this truck is a reclaimer. So the truck kind of follows it, right? You know, putting the hot asphalt into the machine.
Mhm.
And we have a water truck, right? We put in the water in the tank, and they would, as they reclaim, you know, the materials, go polarize the material, they would stabilize the material at the same time and lay it back down simultaneously. I mean, so it's really cool, and it worked really well. So after we done all that, we go back and test it. The results pretty good, right? I mean, especially uh, it doesn't reflect as good, but it's really good. So we've been doing that. So while we're doing that, so when you polarize the whole road, all the drainage would upgrade it, right?
Mhm.
Because the existing roadway cross culvert, 3 or 4 different side, they put it backward, you know, cross culvert.
Mhm.
Drainage will go this way, but the pipe's like this. I'm serious, right? And then the driver culvert, some of them pretty good, most of them like it's just a piece of pipe that just go in there, right? Back in the old day, you know.
Yeah, yeah.
So since we kind of not rebuilding this road, we kind of restabilize this road. I stabilize it. We upgrade all the drainage,
Okay.
all the cross culvert, not all except the bridge, right? Like box culvert, they did along.
So the county would absorb the cost.
Yes. Well, we budget, right? We budget every year, right? Well, we can do so much. So we like to do, the goal is we like to do at least, well, the goal is about 13 to 15 miles a year.
Mhm.
But we haven't really accomplished that yet. Maybe about 10 to 12. So we're still behind. Right? Not just the money, the work. Also, you have the resources, right? We don't have, maybe you need to hire more people or what, more money, right? So we're a little behind. So when we do those projects, so in the design group, and Evan have done one, maybe 4, right? 4 of those projects. But you handle like the whole road from here to there, sometimes like a mile, something like a couple miles, or some of them half a mile. Just depend, right?
Mhm.
We look at the whole drainage to resize all the culvert, like cross culvert, driving culvert. In some area, small, some area pretty big, like a couple hundred acres, right? So maybe 3, 4, all varies, but so we would do the design in how for those replacing all those culverts.
Okay.
So you have to the hydrology, just do it by hand, really, we just make the areas by hand
Mhm.
and find the flow path for the climate concentration, right?
Okay. Yep.
And then to calculate the hydrology. But then Evan, there's a several program you can use, right? You know, and Texas have a little spreadsheet you can use. Right?
Yes.
I'm sure you're familiar with that.
Yeah.
And you can use that spreadsheet to calculate the Q.
Yeah.
And then we also have AutoCAD, Civil 3D.
Civil 3D. Okay.
We don't use it. We have the program.
Okay.
We have the program.
Okay.
And under that, I think it's an add-on they call HydroFlow.
Mhm.
Yeah, I like that program because it's really intuitive. You know, very easy to use, and you can see graphically, right? You can see what you're inputting, and you can do the output. Show you, you know, I mean, really graphic like the culvert or the hydrology, you know, the rational method, or you're using SCS method or TR55, right? It'll show you the result pretty good. And I compare you with other programs, and they're pretty acceptable, right?
Yeah.
You know, hydrology. You use different program, you get a different answer, right? But at least within few percent, 5, let's say 2%, maybe 10, so, and it's acceptable. You just have to use engineering judgment.
Correct.
So we use that program, and then usually we also can use. Sometimes we use HMS, right? I think I saw you on the agenda.
Yes.
We use it like 4 times, right? Sometimes it depends, right?
Yeah.
So I think you use it. I think quiz help you, right? Quiz, right? Yeah.
Yeah.
So we use that, just to get the hydrology, and the hydraulics and we HYA, because, it's a free, you can get it from the Corps engineer, right?
Yeah. Yeah.
And
It's a free, yeah.
Free. And then we hydroflow also do hydraulic. I say some people don't like it. I don't know why. I think hydroflow is really good, but the limitation is they only let you do up to 4 cover. Why, right? It's like
So there's a size limitation there.
yeah, for hydroflow, right? You cannot put if you miss a fifth cover, it won't let you do it, right? I don't know. It well, and usually we don't have that many cover, right? Usually we just size it bigger,
Yeah.
And then that's the 2 programs we use. Or what head grass, right? So we can do head grass. Well, depend when the project in the floodplain, we ought to use head grass, right?
Grass, yes.
In this area, I know it's different than coastal, right? In this area, you have zone A or the AE, right?
Yes.
The A is unstudied by FEMA floodplain. The AE is been engineered and studied.
Yeah.
So if the roadway in zone A, then we still have to do model because we're modifying, right?
Yes.
Over there, right?
Yes.
Usually we'll make it bigger or maybe put in more fuel, whatever the case might be.
Yeah.
So we have to run the analysis, right?
Yes.
And we have a floodplain administrator here in the county,
In the county.
right?
Okay.
And he's like the bookkeeper, right? Of all the zone A study for the whole county, for like developer, consultant, right? When they do all that, they have to submit all that to the floodplain administrator.
Yeah.
So he's a keeper of all those models, right? Let's say, you have a zone A, you modify this culvert, right, to propose. He would keep that model and whoever do it, he keep all the models. So I forgot what the frequency, FEMA would come in, not audit that, but come in, hey, you need to provide all this model. So he would provide all the model to FEMA. So one of these days, if FEMA decided to do the study, right? So here we have all this updated, right? Because before it was like 3 barrel, right? And tomorrow might be a box cover, so right, you have the model. So he would provide that model to FEMA, and FEMA would gather all this model, right? And then do the AE, maybe change from A to AE, right? So when you're in AE, right? So you still have to do the head grass.
Yeah.
And if you modify, if you raise, depending on the floodway or in the fringe, right? If you many modification, you need to do the homer, right? Depend, right? So, and that's correct. We deal with FEMA at that time because they already have the study model, right?
Right.
So I say that to say, so when we do head grass, you can size the culvert, right?
Right.
In head grass.
Yes.
That's what I'm doing right now for one of these roads. Right?
Okay.
So because we analyzing like 8 different costings, right? So, and then Williamson County is really active compared to other neighbor county. I can speak for Harris County, So we just finished the Atlas 14 study, right? I'm sure you're aware of that.
Yes.
Right? So this Atlas 14, we spent a lot of money. It's been going on for the last 3 years, 4 years already. 3, I think at least, right?
Yeah.
Maybe 4. So I have to call it. But it's still ongoing, right?
The Atlas 14 updates.
Yes, update. Right now, as you know, the Atlas 14, we don't have the floodway defined yet, right? So the next task is to have those 3 consultants. I think it was an AECOM, half associate, and do that, right? The 3 work as a team, right? To do this Atlas 14. So you're right, we do update for like development come in, right? Get update.
Yeah.
And on top of that, we're gonna have to do a floodway study. That's gonna cost quite a. So we're working toward that.
Okay.
So speak to all that, the Atlas 14, so we're gonna model. So a lot of consulting, if you do any work in Williamson County, you need to think, we already got the model. We would provide the HMS, right? So you already know the queue, coming in. You don't even have to calculate, just use our queue. then you're good to go. And headrest, if there's one, right, the model, which is provided the headrest, and you can just modify from there, right?
Yeah.
It's existing, you have to do the holes, right?
Mhm.
So that's what I'm working on right now for one of the schematic project for County Road 233, right?
Okay.
So it's kind of north of Gerald, right? It's about 5 miles long, and four and a half, 4.8 miles. So going from 195 to FM 487. So we can do a cinematic to 136 foot of right of way,
Okay.
right? And then the road and bridge division here, we do some small cinematic.
Mm-hmm.
Not like the robot. Like the robot would do a course, F or a J, right? We would go like across the whole county, you know what I mean? For us, more like just one roadway.
Mhm.
We do cinematic. Let's have consulting work on that.
Okay.
They can do the engineering and then do the geometric, cinematic as
Yep.
well.
Okay.
So yeah, Ellen been involved, for those. So basically look at the drainage, right, upsize and all. So she's pretty good. I mean, she's just haven't really done it, right? I mean, previous job, you didn't really do a whole lot, and she's just catching on really quickly.
That's good.
And then, and that's what we use here, right?
Okay.
Just like that. So I didn't mean to like hijack you. That's what you're saying. I kind of, so I kind of situation, I kind of know what we do is, and kind of, so that might help, this training, right?
To tailor, yeah.
So yeah, that's how we do. So like the reconstruction, of course, step to the H&A, but it's the stabilized job. It save a lot of money, right? Think about it, right? We strengthen the roadway, right?
Yes.
You still don't have a payment structure, but at least a design,
Yeah.
reclamation, right?
Recommendation.
Yeah, right, project, right? And the cheaper,
Mhm.
you can go, we go for mile, right? The more we get, better, right? Because it's a big county, right? So we have 1,700, a mile, right? Center mile, right? County road, right? So it's a lot, right?
Mhm.
But then we still try to catch up.
Mhm.
So this stabilize work really well. I mean, it's not 100% rebuilt, but it's gonna last, right? And then we maintain that. And what we do, we put seal coat, we don't do hot mix. It's too expensive, right? So in Texas, called chip seal, right? We don't like the word cheap, cheap. We like to use say seal coat because people's complaining, when we're doing subdivision, the neighbor, the kid, like roller skating, when they fall, it hurt, because those rock exposed, right? The Texas called chip seal. We just don't like the word CHIP, right? Just I don't use that word.
Okay.
Because cheap sounds like it's gonna hurt you more, right? So we just say Silco. But Silco in Texas usually referred to as a fog seal, So it's kind of a little confusing. So we just say fog seal. We don't say Silco. But in Texas, sometimes they call Silco mean the fog seal. When they say chip seal, mean chip seal.
Yeah.
So we do that, but then after that, we just maintain it. If we have crack, and we crack seal it, right? And we might go back. So every 10 years, we go back for another layer of seal coat. So keep the surface basically, so the water will penetrate into your roadway, right? So if we keep that up, so those stabilized jobs should work, right? Theoretically, and see, right? So,
Yeah.
but that's all we can do anyway, right? So because of the money and how many miles of roadway
So
we have to
the
take.
question for you, so you mentioned that the roadway, the right of way split.
Yeah.
So how about, so as of today, so does the county now have isolated right of way for the roadway now?
Well, it depends, right? So like the robot project, yeah, we got free title, right? Right. And the other, have you seen our long range transportation plan
Mm-hmm.
for the whole county? You can go to our website, right, and go to the GIS. You can see there's some blue line and some gold line. Blue line is the control access, right? Like I-35 type of thing, right? So the blue line, I mean, the gold line is the arterial. When we say arterial, like 6 lane divided, right?
Mm-hmm.
So we've been getting 136 foot right of way for
Right of way.
arterial.
Okay.
And when that, then yeah, it's a free title, then county would own, right?
But on the right of way.
Right, but let's say, when some road and bridge project, we might widening, add another lane. So even though before it's a prescriptive right of way, right, let's say, goes here, usually we try to be fair, evenly on both sides. Because you have quite buying right of way from one side, and they say, well, how about me? You know, I want to sell too, right?
Yeah.
Unless they say, oh, I don't want to sell, that's good, that's okay, to go this side, right?
Yeah.
So usually we do half and half, right?
Yeah.
So let's say existing right of way vary from, 36 feet to 60 feet, right? And sometimes 36 feet, can you believe that, the right of way, or the prescriptive right, I should say.
Yeah.
It ranging from one project I'm working on, the 344 case engineering, that's only 36 foot of prescriptive right of way. So it went ranging from that to 60 feet, right?
Mm-hmm.
So let's say that project we're working on right now, consultant working on it. Chris and I, we're managing the project, right? So 36 foot of prescriptive right of way, and now we can get more right of way, right? So when we acquire the right of way on this side, let's say we get 30 feet from them, right?
Mm-hmm.
And get 1 feet from that,
On the other side.
right? But when we purchase 30 feet from this side, we only pay them 30 feet width, right? And what
Wait,
length.
yes.
And then when that happened, the prescriptive right would go with it. So they no longer pay tax on that,
Yeah.
the old 18 feet, right?
Mhm.
This side, right?
Yeah.
So at the end of the day, this whole road is the free title.
Mhm.
So we don't pay them. It's too bad because the prescriptive, they never really own it, even though they pay tax on it, right?
Yeah.
So when we purchase the 30 feet, we don't pay them for the 18 feet here,
Mm-hmm. Mm-hmm.
which is that's a survey they sent me about 8-9 years ago. They changed that. It's automatic, right? Before you have to do a quick claim, right? It's a survey charge. So before when I got here 15 years ago, we have to do a quick claim on this 18 feet with the owner. Basically, he said, okay, do a quick claim, right? The county can claim this land. He just basically, or feet, this 18 feet. But the land surveying board, they have the new rule, right? So every time you acquire something adjacent to it, whatever there before, prescriptive right of way, then we automatic, become, so you don't have to do a quick claim, just minimize the process,
Yeah.
another process, another paperwork.
Okay.
So yeah, to answer your question, yes. So I mean, if have then it would become fee title to us, and then we own the right at that time, right? But not right now, right?
Okay.
Yeah.
Okay. That's good. So then, yeah, CU is a very good school.
Yeah, I liked it. It was good. Too cold.
Yeah.
Came home.
Yeah, she's from Houston area, so I know you get from Houston, so.
All right. And Chris, would you like to share this by yourself?
So in transportation design, where we design mostly PS&E schematics as well. Around 20 years, more than 20 years,
Okay.
private sector, but the last 12 years before I came to the county, I was at TxDOT Austin District,
Okay.
for about 10 years in their central design office. So it was all PS&E production, design, consultant management,
Mhm.
in-house design.
Okay.
So I have some drainage background as well. But taking a step back, I went to school and started my career at the Kansas DOT. And then yeah, and I went to school at
Okay.
University of Kansas. But I spent my time at TxDOT learning the business, learning language, learning, how they do business.
Mhm.
The last 2 years, I was at the division. I went over to the new office that they just opened. And worked in the design division office, reviewing plans,
Mhm.
and then moved over. They asked me to help out with I-30, interstates,
Mhm.
traffic and safety operations, which is mostly dealing with HWA. So I kind of got out of design for sure. And then I got a good opportunity to come here, and the work is totally different. So I'm in engineering services, which is a different department than Con and Evan.
Okay.
Engineering services works with the floodplain administrators team,
Okay.
and we review subdivisions and site plans. And I can tell you in those plans, I'm a lot of meetings as we're going through drainage.
Okay.
And it's just opening my eyes to how amazing it is because there's a lot of development coming up, probably like Houston as well, just building, and then across extremes that are at least 14, which I learned, it's not a regulated floodplain yet. But once the county commissioners adopt it, then it will be. Um, and so having them talk to firms that may not have a lot of experience in that and the county perspective or process is it explains it to me as well. So I see a lot of ponds, they might do multiple ponds, they may do one big pond, they might be trying to separate flow from what's outside upstream to what's already on this site. So I'm learning a lot about drainage from listening, but not doing. So I want to get better at it so I can help cross train. So I'm working with Evan and ORD.
Okay.
So I was in the class with Hassan and my goal is to be able to, I used to be very proficient in my position in geopack. Oh, sweet.
Okay.
But when ORD, I took a step back and start to work on other things. So my goal is to get up to speed and be kind of not bilingual, but be able to work both ways.
Okay.
So I understand the concepts, but it's just how to get from the GIS map and shapefile and a plan sheet,
Okay.
and make sure that if they have to line up for any reason that they need to line up.
Okay.
But for most purposes for the analysis, I know it doesn't have to line up necessarily with planes yet until you move them into the plan set. But at least that's how I think of it.
Okay. All right.
So I'm here to learn all the time, always learning here at the county, always learning.
Yeah, that's good.
Yeah.
So, because we also,
Yeah.
we
Yeah,
learn all the time.
The plan right now, his office, that's why I really liked it because especially my big boss, right, about he's always thinking, moving and shaking. I always try to, get everybody like cost trend in a way best we can. And right now the plan is have Chris instead of having to do 100% review the construction plan for subdivision, right?
Yeah.
And then since they have some design practice, previously from, Geopack, that's what I use Geo, I work for Techstar.
Yeah.
And when I work for Caltrain, we're using Casey, which is similar to Geopack for Casey, that's a program, right? I think Serbia use it a lot, but you can use for all ways anyway. So it's about 20% right now, Chris time gonna help out at doing design, helping design, but 20% of his time, but 80% is still gonna be the plans. That's also he's gonna get just 100%, construction plan review. Because he has some design background. So we should try to keep his skill, updated, right? You know what I mean? Right, especially ORD, right?
Yeah.
And the drainage is the beauty of it about here, this small office here, a small project we did with. If you work on one project, you do from beginning all the way to the end. When you do, H&X, payment design, and you do geometric design, cross section, plan production, put together the spec, unit price, you do everything by yourself, right? That's a nice thing about it. Let's say, after Chris, get trained in ORD, we're gonna assign one project for Chris to work on. We'll only do 20% of his time, but still, right? And then he will do, I know he's done drainage before, but it's been a while back, right? So it might be good to. But anyway, when you do a project, it was an effort too right now, right? And we just go from the beginning, from all the way, right? And even payment design, we can, come up with a payment design, right?
Okay.
And that's kind of the beauty of it. So, and that's what we have planned for Chris right now. So that way, to 100%, right? We can just plan it, right? I know he's doing a good job. I think you liked it. I hope you do.
I like variety. I like learning. I don't want to get pegged into one thing.
Exactly. So, yeah. So,
And every project is different here at the county. I mean, you can say that at everything, but
correct.
you're dealing with people, you're dealing with businesses, people that are borrowing money that have loans, and
Right.
when you're asking them to do something, you want to make sure you're solid on what the regulations are.
Yeah.
Right.
So, well, we have a great legislative team here.
Oh, yeah, we will plus.
It's actually grown. They've added 2 new people, so they're 5 people.
Right. Yeah, but I know I heard it work with, I know you do a lot of Texas projects. Yeah, well, I don't know Austin District, I know you probably usually. So Austin District, we have David Solomon, he's been with us for almost 14 years now.
Okay.
He retired from TechStart, and he's the H&H person over there, and now he's with us for almost 14 years now, so he's kind of like a H&H guru, if you will, right? I mean, he have over 35, 40 years experience. I mean, all he does is H&H. Well, he started out with the dam safety with the TCEQ. What that different name back there, TR and then TR acronym. So TCEQ. It would like move first and start off, and then still do dam safety, which is kind of drainage related, water related, and then he moved to Texas and been involved with drainage all this time.
Okay.
And then we just Chris Wright, I don't know you work with him with a consultant, Chris Wright. He's with Atkins, I think. Well, it's a different name, somebody bought him. Anyway, so he's with us now. So he's a really robust, a lot of modeling and H&H, and he's with us now. He said join us like 7 months ago. So,
Okay.
yeah.
Okay.
But David been with us for a while. They believe that's all they do. Hire we are H&H,
Sure.
So we have a lot of really experienced folks here.
Okay.
We have 1, 2, 3, 5 people.
That's a pretty good size.
Yeah. Kelly Malloy, Steve Richard. But anyway, we have a pretty good size there. So that's why Chris was saying, we have very strong H&H team here too. So,
Okay.
right.
That's good.
So yeah, well, good. Like Evans, can learn. I'm kind of like know a little bit of everything. Not really specialized in one thing. I think I can do roadway, can do H&H, and we can do structure. My background structure. I designed bridges before too. So
Okay.
but when I came to this county, to be honest with you, when I went to Texas, the project's so big, right? In county, there's no way you do everything. It's like here, right? That's the downside. But yes, this project I was part of it. If you can put a hat on it, right? Hang a hat on it, but you only do this part.
Yeah.
Yes.
Yeah, the H&A group, that's the end of all the H&A. They provide the report to you. And roadway guys, me, we just incorporate those into the design of roadway. And that's it, because we don't sign and seal the drainage person do that, right? And the structural same thing. You don't design the bridge, we do a bridge layout. We don't do bridge design, right? A bridge guy would sign and seal the bridge design plans, right? But here, do everything. So I'm kind of a little bit of everything. So I like it, I mean, I wouldn't call myself expert, but good not to be dangerous, I guess, right? It's kind of different. Like Chris said, sometimes I don't want to be like just isolated one thing, but like David and Chris and they just like all H&H. So
Yeah.
From my background, I graduated in 1995 from the University of Idaho. I think West Idaho, right? Well, that's why I am now. When I came to this country, right? 1989, I was telling you earlier.
Yeah.
I was 19 years old. I ended up in Boise, Idaho, which is really fortunate. I have to look back, I was one of the refugees, right? Came over, and we're a group of us, like 18 of us, right? And then everybody go in different direction, right? We flew from Malaysia, and to Hong Kong, one stop, and my dad family is all from Hong Kong. It's kind of cool, right?
Yeah.
We spent a night there. So my uncle came and sponsored me, so I could go out to check. It was before Christmas. It was really cool, right? All the lighting, Christmas was like amazing. Hong Kong's a big city, bigger than New York City, right?
Yeah.
So eye-opening, right? Coming from Vietnam, right? Really third world country, and then you like hang out in the big city before Christmas was like, oh, wow, Well, the reason I say, it's kind of cool, right? But then we stopped in Japan and began no Chinese, right? So in Hong Kong, they all speak Chinese and all the sign, it's Chinese and English, of course, right? And then all the other 17 kids, right? We call kid because it was like 18, 19, 17. I was 19, but
Mhm.
and they all Vietnamese, right? So they don't know Chinese. And in Hong Kong, they were speaking Cantonese, and the sign I say Chinese and English. Of course, I did not know English at that time. So they translating, and it's like, oh man, you are the leader. Everyone like follow me, you know, that's very cool, right? Right. And then it was kind of cool, and I got to go out at the end. The guy said, I, you know. When I go to Japan, I flew from Hong Kong to Japan. This is one stop and change plane. And I said, well, I don't speak Japanese, but I can read half of the Japanese calendar, right? So I think I can maneuver around pretty good. Well, because half of the Japanese is a Chinese.
Yeah.
I mean, like the accent, and it's not exactly, but you see, you know what that means.
I didn't know
And,
that.
yeah.
Crazy.
So I say, well, I can help a little bit, maybe 50%, not 100%, okay? We just stayed there for a couple hours, we played for jam, and then we end up in Seattle, Washington. That's when we get to the United States. I was like, guy, I'm just like you. I don't know a word in English. Me just like you. We just cross your finger, you know, for the best, right? You know, and that's 18 of us. Everybody go to all this big city, right? And of course, again, the big city they had more airplane, you know, to go, right? So we got there pretty early. It's like 8 o'clock in the morning. It was snowing. It's kind of cool. Like first time I see snow in real life, you know, not on movie, right? On movie, but in real life. It was really cool. I thought it was really cool. But and especially in Seattle, it's a lot of pine tree, you know, a lot of it's really pretty, right? You know. So anybody like going off and the big city, right? And I'm here. I'm the last one going to Boise, Idaho. So the plan I'm gonna live until 4:30 in the afternoon. Well, I'm literally there for the whole like 8 hours, right? You know, waiting, you know, and all this kids really gone. I'm just I said, no. So what I wanted to say this because so when I got to Boise, Idaho, Seattle's a pretty big city, not big, but a lot bigger than Boise, right? And especially back in 1989. Boise is a little town, right? I mean, the population like 200,000, right? You know, that's the capital, right? Idaho. That's the biggest city in Idaho. It's only 200,000 people, right? You can imagine. The whole state of Idaho less than 1 million at that time, right? So when you land the airplane, it's a little bitty airplane from Seattle going to Boise, Idaho. It's not too far, really. You can drive like 10, 11 hours, you get there, right? But anyway, before landing, I look, oh my God, well, I'm going. All this tree, I don't see no buildings. All this, it's a lot of tree, right? That's what Boise, I think, is in French. It means like tree, city of tree, right? That's Boise, yeah. It's French, you know. So anyway, and so the reason I say all that, it's really fortunate that I end up there because it's 200,000 people. I went to this pretty good size high school. I was mentioned to you earlier. Because in Idaho, you can stay in high school until you turn 20, right? After 20, they won't let you stay if you don't graduate, right? You have to get a GED or whatever, right? So, and I was fortunate because my birthday is late August, so I could capitalize the summer school at that last late too, you know. So anyway, so fortunately, they end up Boise because the high school went to is nice, it's fourth grade, 9, 10, 11, 12. Right? So about 300 something. My graduation class at 378, right? Just say 400, right? 4 times 4, that's 1,600 kids. Not big compared to Texas, right? Texas high school is huge, you know what I mean? Oh, so it's a big high school, but you come here, like my son graduated, his class like 800 something, like, wow. Good thing I was last in the middle, right? Not, you know. I think sometimes I need to swap one super the heck. I start with a Z. Yeah, I'm not letting you guys wait, you know. So anyway, so I'm very fortunate. So I went to high school there, and people are so nice. The whole high school is pretty good size. I'm only foreigner. I'm foreigner, not Asian. I'm the only foreigner. So they're like they thought I'm an alien from my house. Because I didn't speak English. I said, no, they just thought it was the funniest thing, you know. I mean, they were like open the hand, help you, which is so awesome. just, but I say, so other 7 kids, we still, 17 kids, I mean, other, we're still in contact, right? None of those make it to high school, right? Just because it's a big city, human nature is like lazy by nature, right? You know what I mean? I shouldn't say lazy. You find the easiest path if you can, right? You know what I mean? So in the big city, like Houston or Chicago, or, Washington, D.C., or, San Francisco, Los Angeles. So when you go to high school, I'm sure there's a group of Asian, right? Speak your language,
Yeah.
I'm pretty sure, right? You pretty much tend to,
Yeah.
then your English learning is just slow, right? I mean, right? But for me, I have no choice, right? I say, all the kids, they know each other from like kindergarten because they live there for their whole life, right? You know what I mean? So they start kindergarten and go all the way to 12th grade or 11th grade, whatever, right? 12. And so they already know each other so well, For me, like, I wanted only odd that, right? But it's really helpful, right? So it really get me, learn pretty quick. And then I think a year later, we meet up with a couple from those 18 people group, I would visit them in Portland, Oregon. And one of them is in Canada. Well, not Canada, Chicago, but we go to Canada for a visit. Just a year later, right? And I was like almost graduate from high school. I didn't speak good fluent, but good enough English. I walk up to McDonald's and order thing and like so whatever. Like, they couldn't even walk up to McDonald's to register to order their food just because. I mean, we came at the same time. Right? The perspective, being the big city, right? They were. I'm sure they can do it, but they're just so
Nervous.
nervous because the language is not good enough. They just feel, that's a big thing. So anyway, so I ended up in I went to school there, but we should stay actually first, and then later because they don't have the engineering program there at that time. So University of Idaho is the oldest school in Idaho, or the first university. So they do have pretty good engineering program, not compared to a big school, but they're still a small university. So that's why I graduated from there in '95. So anyway, after that, I move around, so I don't want to take all the time to explain, where. But my first stop was in Salt Lake City. Was a construction company, so Peter Kiwi, right? That time. I got in '95, they had project, and the Winter Olympic 1998, the Salt Lake City, I guess they bid it, they won. I said that they're holding the '98 Winter Olympic in Salt Lake City. They were turning the whole city like upside down. I'm serious. We built 152 bridges, replacing a new bridge, old bridge placement. And what's a design build, right? It's a design build project. Go, 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 And not just like transportation. You got building, right? New hotel coming up, updating on the hotel because they need all the room for people to come here, right?
Yeah.
So it was a really, really cool, to see that. So I worked there for a couple of years, right? And at that time, because the construction experience, it won't count toward your PE experience. Like at that time, now I think they let you have 50%, if I'm not wrong, construction experience. 100, the design you get 100%.
Yeah,
Totally qualified for a PE license, right?
I think so.
So at that time, zero. I said, I don't want to. I want to get my license, but I still engineer. You need your license. Without license, it's just, just like why you become a civil engineer at that time, So I said, I just have to go work for a design firm, So I moved around to different states, work for consultant, and later joined Caltrans in Los Angeles. And then I came to Texas in 2000 and joined Texas. Worked Texas for 10.5 years. And came here, I've been here almost 15 years. So yeah, I managed to start out with Willco. When I was with a consulting firm, I do some design, building design, like development. It's developed. I do commercial, like hotel, like gas station, that kind of thing here. So we do, I do this. So we're with also district, our big boss, Bob Day, he was a district engineer at the district, and he just come around and say, hey, Fan, what do you really want to do for your long-term goal, So I always want to design bridges, I just never had a chance, right? Because I thought I was a roadway, and there you go, I mean, but I thought I was like construction and so on and so forth, and more like transportation, right? So I mean, never had opportunity to design bridges. And then at the Austin district, I think they still have that now. I think the rotation program.
Mhm.
So an office of district engineers, the highest up, I said, I can make that happen. So I talked to the bridge division director,
Mhm.
who will take me there and to design bridges. Less than a month later, I was at the division designing bridges, so it's pretty cool, right? So I do about a year and a half design bridges, and then they will take me through a geotechnical. They have a group of geotechnical in the division, doing like geoshack and mechanical, all the geotechnical stuff, like real geotechnical stuff, right? I mean, and then, yeah, I mean, that's pretty much my background. So a bit of everything. Mainly, I still say roadway. I most of my time I spend in roadway, but then I come to the county. As you know, at Texas, I don't even mess with training because that's a group to do all that.
Yeah.
I mean, I know that it's just from school, right? I mean, yeah, I never really hands on. All the terms that hurts.
Mhm.
So I came here. First day didn't take me long. The first 4 hours. They should I need to learn engineering here, right? Because that's a bread and butter for the county. Especially it's a big county. I mean, it's a lot of flooding, the farmer always complaining something, flooding, drainage issue, blah, blah, blah. I say, shoot, man, I really need to learn this quickly, right?
Mhm.
So I did. I mean, just have to kind of spend a lot of my old time.
Yeah.
And at that time, we don't have that many people here. And now it's like,
You, right?
yeah,
Yeah.
just me and Perrin. Well, he's an engineer, but he's a director of work where they might not sit down do the design work. Right? And Bob is like the director. And Joe England was a county engineer, and he's too busy with the land development side on him. And there's a one gentleman, his older gentleman, his engineer, but he's just like he's almost retired. Right? So when he retired at 70 years old, so when he was here, like 68, 69. So that doesn't really help. He just do his own thing. So I forgot to learn engineering, after hours, weekend, and just try to come up to speed because I need to do it, right? Because I wanted to do a set of plan. I said we'll do everything from the beginning to the end. Nobody gonna do the finish for me, right? The payment design. Never done payment design really, because again, textile, the culture is so big. They were group of payment engineers section, right? They would come up with a payment design for you. You just take that and put in the plan in the cross section and whatever the thickness and all that, but how they come up with it, they sign and seal that report, right? We just take the information and fit it in, right? So for us, more like geometric, make sure that everything's work, right? So yeah, I just have to come up to speed on a lot of things just because, I mean, that's what I kind of, even though now, I mean, we have more people, but we still have that, uh, opportunity to do a bit of everything kind of cool, right? Really, I mean, to be honest with you, because if you've been here for a while, you make yourself really a true engineer. Right? What I mean by that is, maybe that's not the right word, but what is,
Get a lot of skills.
yeah.
Well-rounded.
Well-rounded. I'm sorry, thank you. That's what I'm thinking. Yeah, well-rounded engineer, right? Because you have to, right?
Yeah.
I mean, not just that, the challenge is, I've been telling Evan, I mean, that she experienced it now, and textile, when you do a geometric design, it's a big, mainland furniture, ooh, big, right? But you kind of doing it for a while. You know, kind of work, right? The size, right? But here, the wide way I was telling you, earlier, from 36 feet to 60 feet. So when you try to fit something in, I mean, the ditches have to meander, right? Because you cannot have, because of the highway situation. And then you want to put retaining wall here and there and here and there. Well, we try to get away from them if we can, right? So you have to meander the ditch to make the fun slope work, right?
Yeah.
And we don't put guardrail all the way through either, right? You can, but, we try to avoid that, right? That's what designing work here. We take at least twice as much of the time, the effort, right, to do a textile work, right? Because as you know, Chris, right, textile, the toll, I know you actually, recent Chris came here to Texas. Well, I don't want to say what their background is, because of total, he was part of the LSI group, when we do here. I know you're from Houston, but the Austin area here, all this toll road was led by the LSI group, right? It's a design build. And Chris was part of that, doing the design work. So, yeah.
Very cool.
So anyway, so this toll road, you got all this right of way. I mean, your dish line can really follow your profile in a way, right? Until you get to the cost code, then yeah, I mean, the water have to go drain this way, go this way or go that way, right? But, you don't have to really spend a whole lot of time to, and try to get the dish to work, you know what I mean? It would work, just because of the road. But here, you don't, and then all this kind of strange have, right? It just take more challenge, that's why you can do the project here when you go work with the other piece of cake. No, it is. I mean, yeah, I mean the
Well, it's
length,
big.
the size, right? It's really like construction, maybe half a million, $500 million, $500 million project, pretty sizable, right? Or 50 million, right?
Yeah, it's more of a standard project. Then you have to get more creative whenever you have changing right of ways and
And just a lot of trying to add to it. I just keep working on it until I say, oh, okay, no, I can't. I need to put a wall here. Right?
Mhm.
At the time, I know we need to get more right way, right? So oftentimes we don't get right way, right?
Speaking about that, 332, I do need some advice, because our right of way is a little bit in, and there's not really a way to get around it, it's like 2 feet off the road. So-
Yeah, maybe make the size a little steeper and that.
Yeah, okay, I don't know, we can talk about it,
Right.
yeah.
That's right.
Okay.
So, moving on.
Hold on, are we still recording?
Let me make sure.
So you didn't record
Yeah,
everything I
right.
said, yeah? You didn't say all that because
Yes, I'm
only half
recording.
of them are chewed, the other half is not chewed.
Just making sure, if we do use those a lot, to go back and say, what did they say at this point?
Okay.
Okay.
Yeah, because I know sometimes with the slides, we add on to it. So, but yeah, it should be recording and we can send that.
Yeah, so we can go through these real quick. So training objectives, yes. We're gonna talk about, the role of hydrology in design projects. And then, like we mentioned, yeah, we're gonna cover how the rainfall is transformed to runoff. And then the big thing about the hydrologic response. It's significantly, dependent on the characteristics of your watershed. It could be a wide watershed, the slope, the watershed. It's a linear, very slender, like a long watershed that could also affect the response of your hydrology. So we're gonna also touch on the characteristics, influence to hydrology, and then also we're gonna go over some standard methods to calculate P flows, and then also as well their applications. So session one. So before we go through everything, since we all have some background of hydrology, so we're gonna go through all the terms really quick, so that way, if you know, it's good. If it's really old, it's good to refreshing all the terms. So that's about session one. Okay, so let's go. Okay, so the role for hydrology, as we mentioned before, hydrology is the input for the subsequent, analysis or design work. So the goal of hydrology is to obtain or to determine the runoff based on your precipitation. We will use that as input to size our structure, the culvert, the ditch system, because everything's designed based on, to to provide the adequate capacity to pass a certain, amount of flow. So that's the goal. And then at the end, after everything's completed, the analysis, the design work, then we'll have to also evaluate if there's any impact to the existing condition, or if there's any impact to adjacent properties. So that could also lead to any legal issues as well. Okay. So, Teresa, you want to cover this one?
Yeah. So we started it like from the basics. This is like very going back to almost elementary school. But it is the essence in hydrology. Because when we think about it, in hydrology, we're thinking about the precipitation that's falling, but also not all precipitation becomes runoff. So in our models, we do account for precipitation, total precipitation that falls, but we also account for losses. So when we think of a loss, we can think water's lost through evaporation, infiltration, percolation, and those effects reduce the amount of runoff that we account for in our designs. Um, so so essentially the hydrologic cycle is basically tying the drives the not drives, but ties to the analysis of developing the peak flow. But yeah.
And one thing to add, so in Colorado, the input is not only precipitation, snow melt.
Mhm.
Oh, yeah, big time.
Yep, and you've got to.
In Idaho, I know it's not as much as Colorado. Yeah.
So we here, we only deal with precipitation, but in other states, yeah, rainfall, snow now
Big time.
at the big time, yeah. Okay.
Quick question, what is the percolation on that diagram representing? I'm not entirely sure what that means. I'm thinking of coffee.
So after so water initially infiltrates and like you call it infiltration, maybe I'm not sure about how deep depending on the soil type, you consider water to be infiltrating. But then after a certain point, it starts to percolate deeper into, and that's when you think about recharging groundwater. Sometimes even there's another term for it where it comes out into almost like streams. So it doesn't percolate all the way to groundwater, but it'll kind of turn how the image is showing and recharge like streams on that. So it's infiltration and then it starts to percolate and then it's either groundwater or goes into streams. But usually for our purpose, we only worry about infiltration.
Do we have a copy of this slide? Or do you have?
Yes, I know.
Yeah, because sometimes this will refresh.
So we got a quick question. So when we were preparing the material for this training, and then we can if we should include any, underground hydrology, because there's a lot of aquifer over here in this area, right?
Yeah.
So just a quick question. So do we, in your regular daily practice, engineering practices, do we deal with any aquifer?
Or it's, well, we do for the Edward aquifer here, in this area. And we just have to give the TCQ eternal design. Not really, I mean, we just have to go through the permitting process, right? Whether you in the contributing zone, recharge zone, thank you, Chris, yeah. And then transition, right? Right. And then we just, if the project fall in, with those, and we just have to get the permit application, go through with TCQ.
Okay.
And mainly just looking for just the best management practice, right? Recharge zone, then we have to have I'm sure so have to have a geologist, right? Go out there and make sure did a study, make sure you don't have a car feature or any feature that we need to mitigate or
Okay.
right.
Okay.
And that's part of it. Yeah, in terms of engineering, not too much. I know it's getting anything But yeah, I don't think we will do any extra,
Okay.
One thing I can think of is, what was that case where there was a major karst feature underneath that house? Do you remember? In the water?
Yes, in Roundup.
Was there any way to avoid that? No, it's kind of, I thought it
Yeah,
was a subdivision, not our.
well, no, we enlarge just because the cave is not up, right, it's kind of underneath, it's kind of subterranean, subterranean easement and all that. Yeah, in this area, you have a lot of cave, actually, sometimes, people just haven't discovered it, right? So at that time, the reason we discovered because of water line is along the roadway in the east, county right way. It's a water line, city of Rambler water line, and I guess they had a leak. They didn't know about it, right? So the leaks are getting worse and worse, it's kind of like undermining the whole area to the point, I think it broke in a way, but the water is so much. So now there's a cave just like maybe 100 feet that direction, right? It's like huge cave underneath a person's house. It was scary, right? But I guess still safe, I mean, so when that time comes, right, we have to rely on consultant. We use Kimball is his name. Do you know him? He's like a PhD. Kimball's first name was his last name. Anyway, there's a firm we use to step in when we encounter this because just we don't have the expertise here, right, to deal with it. And usually, oftentimes, stuff like that better. As a county, we're not trying to shut people out. As a county, right, for liabilities, sometimes it's better because if you don't have the expertise, you rather hire third party, right? And you pay them, and not just like put the liability on them. It can look better as a whole, right? And yeah, so when that we just hire firm, right?
Okay.
Yeah.
All right. It's good.
And so then when we translate hydrology into roadway design, we when we think about roadway projects, right, what we're doing is that we're either improving them by widening or we're adding more asphalt. So maybe I don't know. Well, um, and whenever we do those things, we're increasing the amount of impervious cover, right? Meaning that now more rain that falls, or less of the rain that falls will infiltrate, right? So meaning that now how we can see in the picture, there's more water that's not going to infiltrate, and we have to figure out a way to quantify that volume of water to be able to design our systems. Um, and so the key goals in our hydrologic analysis is to be able to identify an optimal outfall. Um, when we think about a drainage system, it's typically at cross culvert locations, maybe into a major stream. Um, but when we think of, like you guys mentioned, like a crossing analysis, typically you would set your outlet as like that crossing location where you have a larger watershed coming in through there. So it's like two different perspectives. Um, and so what we're doing in the hydrology analysis is basically trying to determine how much direct runoff is going to make its way into our system that we have to account for to make sure that our system can convey that much water. And that's kind of like the background of it, to build into it.
Yeah, and also, so we want to design a system that can handle this additional runoff, but we also need to uh, make sure that the release at the end, you don't just let the flow, just the additional runoff just get discharged freely because you have the existing condition in that. So people or the properties that are upstream and downstream, and they because whatever they're receiving is the existing condition. Now you're putting a new road or making a new improvement to the roadway. So we cannot just allow this additional flow to get out of the system and then And that's going to cause, a flow increase in your receiving stream, right? So that will also impact your neighboring properties. So that would be a big issue. So when we design, so we always have to keep in mind that, yeah, we want to be able to accommodate the increase in runoff. But we also need to regulate the release. So
Like detention pond,
it could be in line
inline, okay, like
storage without restriction at the downstream end. So that way we can also regulate the release. Yeah.
Yeah, I mean, that's a good point because here, for one bridge, right, we're talking about, we don't really do curb, like, a storm system. So everything's open channel, yeah.
Yeah.
Right, no, I mean, it's good, so yes, I mean, when you do the storm system, you can do inline, right?
Yeah.
And for us, mainly just do detention, right?
Yeah.
Because we just adopted this a year or two ago, right? We require all the developments, the developer for subdivision, they have to detain, right?
Yes.
Because for development, as you mentioned, right, you got all this
Yeah.
existing land now, just develop the whole stuff. There's a lot of impervious covers and make them detain. So even Tesla, they don't detain, no, the water for transportation, for linear, Texas still does not require for roadway. They don't detain water for the impervious. For transportation, right? But here, the county take that cut up a knot, I said, well, since we require the developer to do it, we have to do it ourselves too. So even on the roadway project, we'd be
Yeah.
acquiring additional area or a right way.
Yeah.
For the detention pond area, so for the symptomatic project, where we have the engineer look into that.
Yeah.
So that way, when we reach out to acquire the right way, we make sure we capture those right way for the pond to be built.
Yeah,
So-
you have time to mitigate your roadway.
Right,
Yeah.
right.
And then also if it's a roadside ditch system,
Sure,
then you want to maximize your ditch value.
right.
So that way, anything that's, additional, then you can put in the pond.
Yeah, well, for TCEQ, if you're in a contribute zone and then recharge zone, right, they make you to do water quality, right?
Yeah.
So, and you can use the pump for dual purpose. You can use for quality and detention.
Yeah.
The same time,
Yes.
right?
Yes.
When you're not in the zone, the recharge, I mean, the Edward aquifer, then we still do detention pump.
Yeah.
Yeah, in Harris County, I think there are some projects where they're trying to implement kind of like regional detention for
Okay.
new railway projects. That's also something that they've been considering too.
So I had to first step out here to take care of a couple of things, and I saw your agenda. I think all this is good, it's kind of refreshing. I mean, I'm also, that's probably kind of good to have this basic. I think maybe good for the HMS. I think we spend a little more time on
Yes,
that,
definitely.
because I think that would be pretty. I mean, this is all good knowledge and all that, right? I mean, we're talking more like practical, like you say,
Yeah.
in school, you take one semester, except for high philosophy class, right? I mean, here we try to do it in 2 days, right?
Yeah.
But I think more here, we all engineer here, right? We in the field,
Yeah, second.
designing, right? I think, like I mentioned earlier, with your hydro flow, we can use the Excel, especially from textile to come up with the Q. I think we don't need to cover all different ones, but HMS, I think was really good.
Okay.
And maybe, spending more time that way, especially Evan, maybe Chris, I don't know how much you know about HMS, Chris, that might be really helpful,
Yeah.
for the new project I mean, Evan or Chris or, can really,
Okay. Yeah.
can be good, so.
Yeah.
I know you say you're gonna have one model or something from it, but maybe more time and maybe do one example, like
Yeah.
how you come up with a queue using the HMS, a different node, right? I mean, I assign them.
So we have a session for that.
Okay, good. I just wasn't, we can spend more time, make sure, they all, come out, like thumbs up or not, they can, Evan can go back to her office and run an expert, to see,
Okay.
Yeah, yes. Okay, so this is just common terminology that you may have seen maybe in reports where you've heard mentioned. You have AEPs, which is your annual exceedance probability, which is the percent chance that a storm of a specific magnitude will occur in a single year. So you'll hear people say 10%, 4%, 2%, 1%. But AEP can also be thrown interchangeably with ARI, your annual recurrence interval. Um, and that's more of like a statistical time description of um, the time between two rainfall events. Um, and then we also have our design storm. So when you think about design, usually they tell you use a specific annual exceedance probability. So they'll tell you 10-year design, depending on the type of structure that you're designing.
So yeah, for the percentage, right? So it's like, so when they say 1%, right? I know it said, annual assistant probability. The way I'm just a typical guy, right? So want to use the lemon language, how is that? Just like
Layman's term.
that lemon term, right? Term, yeah, not language, thank you. At 1%, I think, I mean, like a TED, I got a PhD, I don't have a PhD, right? So it's like, it can be 1% of any given year, right? Because that's what I'm saying, right? I mean, that's the way, right?
I mean,
1%, right, but you could repeat it, right?
yeah, you can have it back to back.
Back to back,
Yeah,
but
so-
but like the way I look at it, okay, here's a 365 days, right? So 1% of that is
It's
what,
like 1% chance every day it'll happen, or?
So I would say.
okay, yeah, let's have. But I want to go, you deal with that, so we
Yeah.
really help everyone now, right?
You're totally right, so I know before, I mean. The term, how many, what return period, each term was used for. I don't know, for the past so many decades. So not until the recent years that people started to realize that, it's it's better to use now the percent, the exceedance percent, because that's a more proper term to use, because to the general public, if you're telling people, well, this is a 500 event, it's 100 event, people would think that this event only happen every 100.
Yeah, that's a misleading, right? When one person, right, complaining, right? I would go out there and say,
Yeah.
well, you're in the floodplain, right? Yeah, because I bought this house with a guy who was flooded.
And
And the guy was 100-year man, so I bought it really cheap, great, because it won't happen not 100 years. That's not how it is.
yeah, so I mean, it's true that if you're talking about over 1,000 years, then on average, yes, maybe every 100 year you will see a storm event of this magnitude. But does that mean that the similar magnitude event won't happen within the year? That's not true. It could happen anytime. So it could happen back to back. But it's just
So basically, 3.65 times a year, is that fair to say, 1%? I mean, right? Is that how I interpret it? So like 1%, right? In every given year, right? So 1 year is 365 days,
Mhm.
and then that's equivalent like 3.65 days, right?
Like
Right. So within 1 year, it could happen 3.65 times. I mean, like you said, it could be back to back,
it could be
right?
back to back.
But I mean, up to 3.65 days, is that the fair?
I would say maybe on the average,
An average, right, of course, right?
given enough time, yeah,
I mean,
if you
that's what I say annual, see, that's like annual exceedance, right?
exceedance,
Right, I mean, I know what the words are, but I just kind of put it in the common, logical thing.
So now if you tell people, yeah, 1%, 4%, 10%, so people can actually feel it, likelihood, because percentage you will, in your brain, you will think, oh, the percentage.
You know, 1% a given year, right? But I say even go dive in deep into what the 1% mean, right?
Mhm.
Oh, yeah, a lot better than 100 year to meet 100 year. What that mean 100 year, right? You know, right?
Yeah, so that's just you can hear these terms, interchangeably. But I would recommend, nowadays that people are very, very cautious about what information you giving to the public. So I would say, yeah, we're leaning towards the percent chance. So that will be less misleading. So that's just the message from this slide.
Right, right. Yeah, Chewy Storm, even that Chewy Storm is pretty good storm in a way, right? For 2 years, right? That's 10% change, right?
Two year,
Yeah.
2 year, it could be
Is it common? It's common to see?
2 years.
Yeah, pretty common, right?
pretty common, I would say. And then most of the roadway drainage system, depending, maybe, I would say maybe 5 year, for your drainage system, this criteria. And sometimes depending on the location, depending on the type of roadway, it could be up to 10 year. If it's a evacuating route, the system we have to make sure that the design is big enough that at least one lane, is passable. So for within the evacuation route. So it's depending on the structure you're designing, the design storm, could be different. Okay.
Yeah,
What year storm was July 5th? You know?
but depending on area, I think the core of it, this was a 5 year,
Oh, wow,
where heat, right?
right. We didn't get a lot of
In
rain.
San Antonio,
Just go,
right?
yeah.
In Curry County?
Yeah, Kirk County.
Kirk County,
Yeah.
yeah. Yeah, that, what a core, what a big eyeball there, it's a 5 year, sure. Even I think it's, yeah, it's a big one.
Yeah.
It, it's an intensity too, right? I think that's what it too, right? It happens so quickly and so,
It's a very short
short
period of time.
duration, right, at the time.
Yeah, so.
Well, I think it's explained there. I think after like, yeah, the change of very specific magnitude, right, can occur in a single year, right?
Yeah, so, yes, for rainfall, I mean, the damage, so I would say either two cases. It could be very short period of time, and then all the rainfall is dropped within a short period of time. So high intensity rainfall could produce a lot of flooding. Another one would be, even though the intensity is not high, but it's long, so you get a lot of about that would also.
RV situation.
Yeah,
where
it's
just like,
it's not going anywhere, so maybe the rainfall itself is not that intensive, but it's just there's a lot of runoff, there's a lot of precipitation. So long duration, low intensity could be very it's very damaging as well.
Okay.
Yeah. Okay.
So a bagel lab, you want to have more bagels?
Okay, thank you.
Yeah.
No, let's take it to the kitchen, so a lot of folks can have it.
Yeah.
Yeah, I think they would hesitate to come in here.
Yeah.
I don't want to like wait until this afternoon is all hard.
Yeah.
Once.
Okay.
Anybody need a break at all?
Yeah,
Take a break.
yeah, yeah.
Take a break.
Well, I'm just asking if y'all need.
Yeah, I apologize, is it a bathroom break or something? I mean,
What I've learned is after an hour and 30 minutes, you gotta get up and stretch.
Yeah.
Refresh.
when I saw a quiz, I took about 20 minutes just talk about that stuff.
Oh, I'm not saying anything.
No,
I'm just saying you gotta get up and stretch. Oh, your butt will hurt. Think monitors. Does anyone need the brush?
No, because I know as soon as we resume, I'm gonna have to go. Oh, our resume is right across the hall. In case you didn't know.
Oh, thank you.
you. And there's a water fountain there too. Oh, the filtered water.
Thanks a lot.
Thank you. Yeah, we weren't sure like how to, when we were setting up the slides, because we didn't really know like everyone's experience level. So we are like, well, let's just start from like, the water cycle and like build it up to actually building like a hydrograph, um, and everything.
I think that's important, when you see a grab, why, think, none of this stuff's lost on me,
Yeah.
so. I'll be right back.
Mhm.
Sounds good. Your coffee, I think, was.
Hey, get my paper back.
Yeah, I've always been in like smaller companies. So kind of like getting thrown into like different things and it kind of like it's a steep learning curve, but then it's like still nice to get exposed to everything
Yeah,
at once.
yeah. I found like with engineering, it's like there's just so many aspects to every single thing. It's just like
Yeah.
having a little bit of context goes so far,
Yeah.
I think.
And good mentorship too.
Yeah, so I really like working here. Constantly putting us through trainings.
It's more environmental science or environmental engineering.
Environmental engineering, yeah. So, hydrology and some soil science and a lot of pollution, which doesn't get used. But
Yeah, pollution.
yeah, I was like, well, I can go into oil and gas or civil, and I was like, I'd like to live with myself. So, yeah.
Like water and wastewater treatment.
Learned about it, yeah. But we don't really we have our environmental division that does septic, but other than that, we don't really handle utilities like that. So yeah, they did set us up a tour to go to because we had some summer interns. And we took a tour of the Round Rock wastewater treatment plant for them, so that was fun. But yeah, I don't know. It's really great working here because they just so many field trips and trainings, and we went to go see what was I should know. It's a lime, please, lime plant. Yeah,
Down south somewhere, right?
yeah.
Nebraska.
Went to go see like literally like where they mine and do everything with lime. And
Wow.
yeah, it was really, really bright there. Everything's just coated in lime everywhere. So you're like dehydrated and it's hot. I learned I never want to do mining. Terrible. But yeah, anyway.
Okay. Do we wait for Con or okay?
I think he's gonna come back later.
Okay. Okay, we can keep going then.
I think he said that, right?
You said that, yeah.
And then now here we have rainfall depth, which basically tells you the rainfall depth at a specific time for a specific storm event. And then we have our rainfall intensity, which basically tells us how much rain fell throughout a period of time. And then here we just have a general term of the NOAA Atlas 14. Um, these are the new rainfall data updates that were released and were implemented in 2018. So typically this is where we would get our rainfall data sources, although whenever you're working on projects, you should always look at your local jurisdictions because they have their own rainfall data that they want you to use. Um, and then we have here runoff, just like general term runoff. It's basically any rain that did not infiltrate, that we didn't lose, that we have to account for that's going to flow into our drainage systems or into our streams and channels.
You know, sometimes people call it direct runoff.
Or direct runoff, yes.
Yeah. Right.
And then, so we always hear about peak flow, calculate the peak flow, Q. And it's basically the maximum runoff rate within a drainage area or within a watershed. So it's in our units are CFS, and we are going to get more into it in further slides, kind of breaking that down, what that really means. And then we have our runoff methods, and these are the methods that we use to calculate that peak flow.
There's construction going on.
You're good. And so with the runoff method, we can either, or depending on the runoff method, we can calculate our single maximum peak flow, or we can calculate a flow time history. So basically a history telling us how the flow changed throughout time for a watershed or for a drainage area. Here we have watershed, and that's essentially a drainage area. When you think of a watershed, it's more of a bigger drainage area. But essentially watershed drainage area, you can think of it as a equal term. So, and then we have the rational method. So the rational method is one of the runoff methods that we can use to calculate peak flows. And that's what it does is that it transforms the rainfall data that we obtain from these different sources like Atlas 14 or from local jurisdiction data to develop the peak flows. And so those methods have their own formulas that incorporate that in to give us an estimate of direct runoff. That makes sense. And the rational method is typically used for drainage areas that are less than 200 acres. And that's based off our TxDOT hydraulic design manual. But depending on where you're at, it's always good to check what their criteria
In
is.
general, so sometimes people will say, well, what about 201, 202? I would say, yeah, you can still apply. And then, so one thing about rational method is it's a empirical or it's a formula that was derived from a lot of experiments and what we should, the for rational method, the watershed initially, the background of the rational method is that the assumption is that the watershed is homogeneous. Okay, so the characteristics should be pretty similar, and there's not much storage in your watershed. So that means that rainfall it will all come out. That's the assumption behind rational method. So if you notice that your drainage area there's a lot of pockets, there's a lot of storage, then you'll probably reconsider, the way that you derive your runoff review, because considering that the storage effect, the actual flow that's coming out be less because a lot of things will be, held within your storage. Okay.
So does that mean, I've seen some examples where looking at the aerial, it looks like farmland and it looks like they built contours for erosion
Like the
Protect-
terracing,
terracing. They built terracing. Would that be a place where the rationale would be questionable? You know what I mean by terracing?
Like.
On the farmland, they build,
they like try to keep as much water on the property as possible, so they'll
Oh.
build it so that it like kind of,
There.
it's really hard to delineate, but yeah.
Yeah, that you probably need to reconsider because a lot of water will be held back, right? So I would say if storage is a big consideration, then I would, uh, instead of just doing just a single value peak flow calculation, I would probably run like a HMS or some sort of, uh, software packages that will consider the storage effect. And then you're talking about storage effect, time becomes very important. So it's no longer a spit out a single value peak flow, but you do need to consider the time history of the flow. It would be a resident time in that feature. How long the water will be, staying there and then will be released. So that will be, I think, a more complicated or more advanced approach will be needed
Okay.
to consider.
And when you say like, I guess like the underlying assumption being that it all just goes down, but you run into, like in some of the delineation projects that I've run into, like the farmers, there'll be like a natural flow point where everything tends to flow. The farmers will dig out a pit just for the cows, and then it
Yeah.
kind of goes through. Maybe there might be one of them, like how do you cut that distinction between like I need to go to another?
If the pond is not that big, or if it's not that deep,
Okay.
or then you can probably ignore, or you have to kind of check the water, if the pond there's always water in there, or every time, there's an event, it's always dry.
Okay.
Yeah,
Yeah. So if it's like filling the whole thing versus like just kind of.
yeah, if it's always like they always keep some water in there, that means that the available volume is already occupied.
Okay.
So whatever additional flow, it will not go into that storage.
That makes sense. Thank you.
Sure. All right.
And then we have runoff coefficients. You'll also see it as like a C value. And it's basically a coefficient that represents like the percentage of rainfall that would become runoff based off of percent of rain from a storm event that would become runoff. Um, and you have different values for different surface types. The higher the C value, the more impervious the area. So when we think of like concrete, we'll think of like 0.9. When we think of grass, it's maybe 0.35. But these values also, there are guidelines, but then sometimes there is like engineering judgment that comes with it. And that's a part of the rational method. And then we have time of concentration, which is the amount of time that it takes from water from the furthest or from the most hydraulic furthest point of a drainage area to get to its outfall. And that's when we think of longest flow path and developing that and analyzing the contours.
Sorry to interrupt.
No, good.
Something that Con is always like, I will find the longest, I'll draw the basin and then get the longest path, and then he'll say like, but that's not the most distinctive path of the basin, because it'll go like around or something.
Mhm.
So do you just pick the longest one each time, or do you also like factor in I don't know the word he uses, like it's not the most descriptive of that base. Am I making sense?
Descriptive.
Like, if you've got like, a bit, call it a circle, right? The longest path might be like around the circumference of the circle, but he says like the one that goes through the middle will be like the most descriptive
okay.
of like where,
Like how water truly flows, I guess you could say. Like water's not gonna make a right turn and
yeah,
come down.
I would, yeah, because if you really, yes, if you were trying to, I know, I mean, you drop a water, droplet, yeah, there's many ways for it to get down to your outfall, right? So by definition, yeah, the longest time you could go like this, then before it gets out, right? But then the way I see it is you also need to think about, efficiency, right? So how, you know, the universe works, right? So for everything to happen, um, the matters would try to find the most efficient way to occur, right? For the phenomena to occur, right? So you drop the water, yeah, it will tend to find the slope with the higher slope, and it will find its way, the most efficient way to drain. So it wouldn't go like I'm gonna climb up, I'm gonna make this
Yeah.
turn. So it will find the most efficient way to get to the outfall. Yeah, so so yeah. So I would, in this case, I would agree with Khan that you would try to find the most efficient path. Um, and then also, I know, since the formula is very, I mean, for rational or for this type of work that for roadway projects, since there's so many projects, I mean, from county work, textile work. So, so many studies have been performed, so you kind of know, uh, usually there's a ratio that say, okay, this is a roadway, type of a community, let's say the subdivision, it's all undeveloped area, uh, just by the the studies that have been conducted, you kind of know, okay, what is the ratio, Q over area. So it'll be like undeveloped. It could be, you would think that the number would be probably below 1 or 1 or 2. But if it's a developed area or subdivision, it could be like a 5, CFS per acre. So because these are common features, right? So you kind of, if you want to really check, if your flow is coming out right, then you can divide it by the area that you are calculating. And you will see, well, if you see like, in a highly developed area, and then you see the ratio is like below 1, and that's kind of, so definitely maybe you're underestimating. Yeah. So, right.
And then we have the NRCS method here, which is another runoff method to be able to calculate the peak flow. And this is for areas greater than 200 acres, but less than 2,000 acres. And the NRCS method uses the curve number. And the curve number is what accounts for the soil type, the land use, and the soil moisture. And that's the part of the equation that helps determine true rainfall runoff. And then we have hydrographs, and the hydrographs are a time series of how flow changes over time for a specific drainage area and watershed. And we're just generally introducing these terms that we'll talk about and break down in further slides.
Okay, so session 2, so we're getting into the rainfall runoff transformation. Okay, so the entire process, we of course to first identify our watershed. So once we define our watershed, then we can start derive all the the hydrologic parameter, that's associated with that particular watershed. So it could be the parameter that, that is related to the geometry of the watershed. So like we mentioned before, the shape of the watershed, slope, and then also the cover and everything, all these properties, the watershed will have to be quantified first. And then once we have everything prepared, then we can start looking at, okay, so once we drop this amount of rainfall over the watershed, how do we, what would be the approaches that we, or methods that we would utilize to convert this rainfall to runoff. So that's the, and then the last one, like, we will look at the, different characteristics of the watershed, how that would affect, the shape of your hydrograph, or the runoff, direct runoff hydrograph. Yeah. Okay.
So here we're looking at what a watershed is. I'm kind of delineating what a watershed looks like. And we identify those watersheds by looking at our high points, and selecting an outfall. And the runoff within a watershed is gonna act differently depending on the surface slope, the land use type, the soil type, the shape of it, and also the storage that's available in it. When we think of the surface slope, when we think of like these hills, water is gonna run off a lot faster. It's steeper, right? So it's not like a flat area where water will really have to pond to be able to finally move. When we think of land use, depending on the type of surface that we have, it could slow down or speed up water. When we think of concrete, water runs off faster versus in grass, it's a rougher surface. Soil type, some soil types can absorb more water than others, so that will also influence the amount of direct runoff that you get. The watershed shape as well. That's more so like a timing effect, I would say, depending on if it's a wide watershed, or if it's a like an oval watershed, it'll react differently. And also your storage effect. And that just depends on the terrain of the watershed. Um, and I know that typically in the engineering world, it's not as simple as delineating a watershed like that. But that's just a general example of what it looks like. So we have our high points around, and we have our valley or stream down the middle with an outlet here at the bottom.
Okay. So before we move on, a quick question for everyone. So question is, so will watersheds interact? That means that will water, come across the borderline determine to divide or not?
At the outfall or no, like,
Well, I mean, I would say, not necessarily an outflow, but I mean, there's a possibility that the water, let's say, from this watershed will get to the next one, or the water from the next one will come over.
I wanna say no, but I feel like that's hypothetical, I don't know.
Yeah. All right.
Well, the boundary that you have are their high points, so that the adjacent one that would flow into it has to be higher to come into this one, I would say, unless there's a stream pouring into it from the other one, or it has a wide connection, if that makes sense.
Yeah,
But then even then you would change your boundary, so
yeah. So I would say, yeah, theoretically, it shouldn't, right? Because the high point, if you drop the water, everything should be coming towards the low point, and then on the neighboring watershed, everything should be also going to a certain outfall. So in theory, that's true. But in reality, it also depending on if the water from your outfall can be released freely, right? So let's say if there's not adequate conveyance downstream from the outflow, so water's not backing up. So then, if your watershed is really full, then the flow will start cascading. So that happens a lot with your roadway drainage, right? So example would be, you have surface, you have up and down, and then along your roadway, right? And then everything will be flowing towards your sag inlets, right? So your high point on the roadway will be your drainage divide. But whenever, let's say, the runoff is exceeding your sag inlet capacity, so the water it's gonna going to start ponding on your stream, and it gets higher and higher, then it will definitely go over your drainage divide. So the cascading on your roadway will start happening. So that's yeah.
Yeah, and that's why sometimes you'll see like for drainage design, you'll see a higher storm event design requirement for like low conditions for depressions. For that same reason where water there is gonna just pond more and it's a low lying area. Okay. And so here's just like a general slide of recognizing contours. So whenever we see a circle like that, it's typically a high point. And the way I like to think of it is looking at the elevations, we were to drop water here at the top, um, where would it, where would her water drain towards, right? So physically, or when we think of physics, water is going to go from a high point to a low point. So it's going to try to follow these ridges. So whenever you see these V points, it's like, okay, well, this is a high point, and this is like the downward slope of like a hill or a mountain. And water's gonna flow this way. And then on this side, we have like an inverted contour here. And when we think of it, this is a high point here. And then if I were to drop a water droplet here, my water's gonna come down this way, down the middle. And we'll see right now on the next slide, we have like a cross-sectional view that kind of explains that a little bit better. So, so here, we have both a ridge. So when we say a ridge is like the high point of the watershed. And when we think of valleys, they're the low points, right? So the valley would technically be the stream, where your stream would be, I guess. And if we were to plot this, if we were to cut a cross section here across this mountain here, we know that this red point is at the 850 elevation. And then here it's going up. It's now at 875. So now we know that the terrain is going up. And then at this point, it's coming back down to the 850 elevation contour. So now we're at 850. And then we're coming back up and then coming back down. And so when you look at it, when you compare the plan view to the cross-sectional view, now you can really see that this here is that ridge, here's another ridge, and then here's that low point. So if I were to drop water here, anytime you want to delineate, you always delineate perpendicular to the contours. So I would come down this way if I was delineating a high point. And then if I was going to delineate my low points, it would be down this way. Does that kind of make sense? And here's just like a general step if you're gonna delineate a watershed. So first you would identify your outlet. So you want to say at this point I want to know like how much water is coming through here. And so you identify your outlet. And here we can see that there's two streams coming together. And in your next step, you want to identify those high points because you know that that watershed is going to be bounded by those high points. So here, every X identifies our highest points that are on this topographic map. And then next, you want to identify ridges and valleys. So I can tell that um, by looking at the contour lines and by looking at the intervals, that water is going to come from this high point, come down this way. And then here, it's a little, I'm between two high points, right? So water is going to go down this way, but then also it's like a low point, like a valley. So water is going to either go this way or this way here. But I still want to follow the general ridge point, so stay perpendicular to the contour. Here I have another ridge. I can tell that this is the water's coming down this way. And then here I can tell that there's another high point. If I delineate along that. And now for the low points, I can tell that here I have that inverted V, we could call it. And those inverted V's are typically your valley points. So I know that if this is a high point, my water is going to go this way, it's going to go this way, and it's going to go this way. But my focus is this outlet point. So I only care about what's coming down this way. So I have one stream, aka one valley, and then I have another one here. Um, was that good? And then in your last step, you tie everything together. So when you think of a watershed, you follow high points, right? And those valleys, I'm sorry, those ridges that we had drawn here were the high points where hypothetically water shouldn't come back. Water from this watershed shouldn't go this way, right? So then we close it like a loop here. And now our valleys are the streams that will carry that water to the outfall. And so here we just have like a general example, which I think I might. So we were to do this, our step one was to identify our outfall, right? So let's say that our outfall is this location. So where these two streams converge, right? And then we have to identify our high spots. So where would those be? Any suggestions?
Like to the northwest, there's like that tire bridge.
So this one, right?
Yeah.
I'll put an X. And then do we have any more?
There's like one directly west.
Directly
Like,
yeah.
it's like this one.
So this one, if we look at it, the highest point within this one would be this high point. Because this is like the isolated circle point, and from here you can tell that water's gonna come down this way. So you want to look for those isolated circles like these, because you know that that's like the highest point where water's gonna come from. Really. So, for example, like this one would be another one. Um, gosh. And
And there's another one too, that says 1,000.
this one.
Yeah.
And then there's a few more, but I think considering the outlet point, these are the ones that are closest to it, surrounding it, bounding it. And so now we want to identify the valleys. So the valleys are the high points, right? The valleys are what's going to bound the drainage area, the watershed. Here the topo map kind of helps us because there's already a stream, meaning that that's going to be our valley. So when you think about it, if I were to come down this way, right? Because when we delineate the ridges, we're thinking about the V shape, right? So this is that general V shape here. And if I were to bound it here, if I were to follow this general V shape like this, what would that mean for this stream? If I was to say that only water north of here comes this way, um, is that truly what's happening at the outlet?
No, because the outlet has that southern stream as well.
Exactly, yes. So it is a ridge, but it might not be our bounding ridge. And so when we think about it, we can kind of go through and identify all of them, but then you have to step back at the end and really see which ones are the ones that are going to bound your drainage area based off your outlet location. Um, so where would our next ridge be, I guess?
Between like the other two X's.
Correct. So water would come down this way, this, this, and then here, what's happening here?
It'll flow like either way,
Through there.
but there's like a valley on the ridge. Yes.
Yes. Yeah, so it'll kind of come this way. Um, it'll meet here. And even though I'm not following the general, like I'm not following that inverted V anymore, I'm still gonna keep going because essentially any water coming down this way now, right? This is like a low point. It's either gonna come, water is either gonna flow to the inside or towards the outside. So I'm still gonna draw it as a ridge here. Um, and then here, I'm gonna keep following that V point and extend it generally like that. And do we have any more?
Going like south of that, like the X over here.
South of X? Yes.
Yeah.
So we have another one that follows here. And thinking about the outfall, where what seems like the most logical way that um ridge that would bound for that outfit, if that makes sense.
Yeah, like the peninsula kind of thing that goes out.
So this way. Oops. And then here, I can either maybe go this way, and it looks like I can kind of go this way. Um, but what way seems more realistic in terms of the outlet? Right. So come up this way like that. Because if we think about it, this is another ridge. So water's gonna go this way, and it might still make it into this stream and make its way to the outlet. But the water on this side is already gonna come down this way. Maybe it'll overshoot and miss the outlet a little bit. Um, and then for valleys, when we think about our valleys, let me see if I can change my color. We already have the streamline here, kind of showing the valley, but when we look at valleys, we know how to identify them on the contours because they're the inverted V's, right? So water's gonna come down this way, and it's gonna follow that inverted V pattern, right? And so here's one, this, and then we have another one here, right? But it's maybe not like a mainstream. And we have a few, but those are like the general ones. And so now that we have those ridges and we have that valley, we can kind of finish closing the loop here and say that all the area within this boundary is going to drain this way. Except here, we should close this a little bit better because similar to this situation, the water here is going to come down this way. This is like a valley, and it's going to make its way to the outlet. But eventually, some of this water here is going to overshoot, and it's not going to fall into. It's going to make its way into the stream after the outlet location. So maybe I'd go something like this to kind of close it and assume that that's still coming this way. Does that make sense?
Mhm.
Is that good?
Mhm.
Yeah. Yeah. So that was kind of establishing watersheds.
And so that's just that was just the concept. So now everything that we just went over, is done in GIS because you will have LiDAR, right? You have your terrain models. So in GIS, in that, the process can be, really sped up.
Mm-hmm.
So that's why we really need if we can get at least like 1 or 2 licenses. So all these processing work for you guys can be really time saving.
Mm-hmm.
So everything's based on the terrain, so this GIS would be the best tool for that. So next one, so we're going to talk about precipitation. So we can quickly go over the sources. So in general, all the rainfall, the precipitation is measured or collected by, rain gauges. So gauges, we will consider it as, point measurements. And this is physically based because you're actually collecting your rainfall. And then we also sometimes you can hear people refer it as ground truth because you really like measuring the rainfall. But the thing is, since it is point measurement, and if you don't, let's say your area, your rain gauge network, the density is not high enough, you wouldn't be able to capture the spatial variation rainfall, right? Rain gauge over there, the other one is like several miles away. So what happens in between? You won't be able to know the information, right? So unless, let's say in your area, your county, a very high density network is in place, then you will be able to know or to learn about the spatial variation between. Okay, so that's the characteristics for gauge measurement. But then you also have the so-called radar rainfall, or even satellite rainfall. Rainfall information is a byproduct derived from satellite imagery. Okay, so these two, radar and satellite, they are sensor based because they don't actually measure rainfall, but they use the reflectivity information to estimate the rainfall information. And then for radar rainfall and satellite derived rainfall, uh, since it's not physically measured, it's sensor based, therefore accuracy is not as good as the point gauge rainfall. However, since these are like sensor based measurement, and then these two usually comes in a gridded format. So from the information provided by these two data sources will give you the spatial distribution or the spatial characteristic of a particular event at a particular time. Okay. So nowadays, I'm pretty sure in the Austin area, services have been, established to basically call this a so-called, radar gauge, coupled or, radar or gauge corrected information, uh, in which, the radar rainfall, which, preserve the spatial variation or spatial characteristics of the storm event, and then they will compare that against the gauge, information to see, let's say you have this particular cell, and then there's a gauge right there, and then from this, gridded radar information on top of that, another, gauge location, they can extract, that particular point, the gauge measurement versus the radar, and they can tell, oh, it's really far off by how much, and then after the comparison, then they can apply an adjustment factor to your radar rainfall. Let's say we need to use our radar estimates by, let's say, 10%, 20%, depending on, the bias, they call it bias, or the error, how much error, is observed. Then they can adjust the radar rainfall. So a lot of counties already have, the gauge. The gauge is just the, radar rainfall information for all the government agencies to use. So that's just, a little, concept about, combining both, point measurements, and also, the gridded format, gridded rainfall. So you can pretty much combine the advantage from both sources together.
And then these are just like general rainfall data sources. Here's the NOAA website link, where typically you can gather your rainfall depths and intensities from. But for example, here we saw that Williamson County, the subdivision regulations, they do have their own preferred rainfall depths that you would refer to for those type of projects. So it's always good to check local jurisdictions for that information.
I always get confused between this table and like the idea or something. I always get like if we could go over that at some point, like what the difference is, because I always get them jumbled. But yeah.
Okay. And so then we think about design storms and actual storm events, right? So design storms are what we use to design our storm sewer systems. And it's basically a hypothetical storm that's made to simplify things in our analysis. But then when we think of an actual storm events can vary, right? So a design storm event, we simplify it so that we have a, a maximum intensity around that. But when you think about a real storm event, sometimes it can start raining really hard, sometimes it stops and it fluctuates like that. But for our purposes, in our hydraulic analysis, what we develop our design storm events to better simplify that analysis. And here we can kind of see how that differentiates. So on the left, we have an actual storm incremental rainfall graph. And then on the right, we have one for design. So we can see how in an actual storm, different amounts of rain fall at different times and it ranges, it increases. We see almost like two humps here. So we could say that this is one, and then it stopped again and again, versus for our design storm, we have just one hump here. And then
In the design storm, the shape, where the center of the mass is placed. This one in particular, this is like a center of the mass is placed at 50%. And depending on your location, so design storm is not just like a randomly built, it's a product that's based on statistics. So at the particular location, you will look all your historical events for different small one to big one, different duration. Then you by going through that, of course, we don't engineers we don't really spend that effort to do it. Usually, this information is already prepared by some scientist or from from a particular project that maybe they do it a while ago. So they will look at different storm characteristics, and then they came up with this. Okay, so in our area, and for what rainfall magnitude, usually the peak, the center of mass usually comes in, let's say maybe 33% of your storm duration. That means that it's all the rain will fall hardest the maybe front part of the storm. And in some area, it could be 50%. It's a very evenly distributed. And in some area, yeah, let's say maybe in your neighborhood or in this region, typically when you see a storm, the heaviest part, it's probably the latter part of the storm. So then the weighting can be shifted. So, but the purpose is to have something that's representative of your area and that's also simple enough for engineers to use for the analysis purposes.
And is that like, I might be misplacing this, but there's like a map of the United States that had like type 1, type 2, type 3. Is that's it? So
Yeah.
do you look more, when you're looking at this, do you look at like local jurisdictions or do you just go by like big regions? Like,
You go for local.
okay,
So you would, depending on your area, so if there's no, so I would say you first look at county regulation. Because county regulation should apply for a bigger area within the county. Then depending on your project, let's say today is a city of Round Rock. So it's a smaller area within county. Then the city criteria will govern.
okay,
Okay. So for Georgetown, then you would look at if there's any predefined criteria for Georgetown, then that will govern.
okay.
If it's an incorporated area, there's no higher governmental entities, then the county criteria will be applied.
Okay.
Yeah. But in general, I would say all the governmental entities, they should coordinate with each other. So it wouldn't be like, oh, you say one thing, I say another. And usually that's not the case.
Okay.
Yeah. Yeah.
Yeah. And so here we just have kind of like differences between a design storm and an actual storm. So the design storm is more of a statistical product. Once again, to simplify, and it's more convenient for our design purposes. And it does assume that the entire watershed, that the rain over the watershed is uniform. So unlike an actual storm where it can be raining in one part of the city and then not on the other side. Um, and for the design storm, we can separate it into those AEPs. So we can say, 1%, 10% probability. And our actual storms, that's more of like when you think of an actual storm event that happened. So like you said, Harvey earlier, that would be actual storm event data. But that doesn't really represent what happens overall in that region. That's just a very specific event. And that's why our design storm is more of a statistical product that's a more general um, rainfall data of what really happened in the area.
Yeah. Do you mind taking a step back real quick to the previous slide?
Mhm.
I just want to ask the question about the horizontal axis. So on the one on the left, it says time in hours. So the 55 is actually 55 hours. Is that, or is it actually minutes? See how it says 5, 30, 55, 80?
Uh-huh.
Are those, so 80 hours is multiple days? Is that correct? And then I guess what I'm getting at is on the design storm,
Mm-hmm.
I see 12. Does that mean uh 12, like 12 hours later? And so I'm trying to relate the two at the bottom. Oh, the axis is non-related or
Oh, they're not, I don't, yeah, they're not related. So these are just two examples,
Yeah.
you know,
Oh.
to show that, oh, in the
Okay.
design storm, you know, the duration is usually specified.
Understood.
Usually that 24 hours event. So.
Two separate examples.
Mm-hmm.
Two examples.
Okay, I thought they were
Really
just
trying to-
Yeah.
To show that, yeah, for actual storm, you can have multiple humps, right?
Yeah.
Okay.
And this is the actual result from like the HMS product,
Uh-huh.
where it's actually like a clean design one hump,
Yeah.
incremental rainfall graph. And this is just like a general um graph to represent how intensity can change in an actual storm event.
Yeah. So they're not equivalent or they're not related.
Mhm.
Okay.
Yeah.
And so here we have so rainfall depth is the accumulated rainfall to analyze how depths change over time. So for example, if I'm saying that at 1 hour I have, or I'll use the examples at hour number 2 of a storm event, I have 0 rainfall depth. And then at hour number 4, now I have 0.5 inches of rain and so on, right? And this is kind of like we can translate this to the data that's provided by those local jurisdictions. So if I go back over here, when we say at 5 minutes in a 2-year storm event, I have 0.52 inches of rain. This is a more simplified example, but we're basically gonna go through and develop a Hayato graph that will really show how the intensity um, to show the actual total rainfall that fell based off the changing intensity as the depth changes that fell. And we'll run through an example right now.
Okay, I was like.
Yeah. We'll run through an example.
This part gets confusing to me.
Yes. Yeah, that's why we added like a basic example, but then there's still like a general kind of more how HMS interpolates a result.
Yeah. So you were talking about the type 1, type 2, type 2, type 3. So that's related to this curve here. Usually the term for this type of curve, they call it a S curve. So type 1, type 2, and type 3, each type has a different weighting. So I forgot which one is which. I think type 2 is 50%, so your S will look symmetrical. Yeah, and then type 1, I think the shape is a little bit different. And type 3 shape is another type. But the difference is, you know, where the mass of the rainfall is placed. Yeah.
And then just to keep in mind here that the goal from the rainfall depth data is to calculate the total rainfall that fell within a watershed. Because this rainfall depth is only telling us its depth at a certain time, but that doesn't mean that there was a total of let's say if I was to add all that rainfall depth, that's not the total rainfall that fell. That's just how the depth changed throughout time. So from rainfall depth data, what we really want to get is our rainfall intensity. And hyetographs are what represent that. So on the left here, we have that rainfall depth plotted, which is also called a rainfall depth mass curve. And on the right side, we have the hyetograph, which is your intensity versus time. So the mass curve is your rainfall depth at a specific time, right? So at hour number 2, my rainfall depth was 0. But then on my hyetograph, that time on the x-axis, is actually the time interval. So I'm saying that at the second time interval, my rainfall intensity is 0.25, say. And we're gonna walk through and transform that mass curve into that hyetograph to get our total rainfall depth. Okay. So this is the first step, right? So this is the raw data that we collect, let's say from like a local gauge. And it's saying that at hour number 2, our rainfall depth is 0. At hour number 4, now I have half an inch. And what we really care about is to determine the incremental rainfall. So how much more rain fell between time 2 and time 4. So here on the graph, the table that's on the right, we have our time interval, right? So they're even time intervals. We're saying that at our first time interval, 0.5 inches fell. And we get that by subtracting the rainfall depth at time 4 minus the rainfall depth at time 2. And so then we go on and develop how much more rain fell during each increment, if that makes sense. You guys follow? So for example, what would be my next incremental rainfall after the 1.8? I guess what would come after? Oops. Here.
4.4 minus 2.6. I'm not amazing at mental math, honestly.
No, no, me either. You're
2.2. 2.2.
So which ones, which values are you subtracting?
6 and 4.
4.4 minus 2.6.
4.4.
Or am I
Did you take out the one?
on the wrong level? Yeah.
Yeah, so it'd be the 4.4 minus 2.
Oh, wait. 6 minus 4.4. Right?
It's 1.6.
So 1.6.
I think it's time interval 12 and 10.
Yes, 12 and 10. And we know that because, so think of it as if we're thinking of this is in terms of time interval. So this would be our first time interval, second, third, fourth, fifth. And we're looking for the 1, 2, 3, 4, fifth time interval. So 1, 2, 3, 4, 5. So we would subtract this data set here. So 6.6 minus 4.4, and then the 12 minus 2 would be the next value here. And we have the equation here. It's kind of, you can go back and maybe digest that a little bit better, but it's a little confusing. And then in step 2, this is the full table developed from the last slide. So our time interval versus incremental rainfall. Sorry, this is still our rainfall depth data. Just put a copy of it here because we still need it. And then this is the fully developed time interval versus incremental rainfall table that we saw on the last slide. So now that we know how much rain fell during our time interval of 2 hours, we can calculate our rainfall intensity. So our rainfall intensity tell us the rate at which rain fell during that interval. So we divide that incremental rainfall by our time interval. So 0.5 divided by 2. And that's how we develop our rainfall intensity at each time interval. Does that make sense? And so now we can actually develop or draw our hyetograph. So we went from our time interval, our incremental rainfall, to then get our rainfall intensity. And this is the plot of the hyetograph. On the x-axis, we have that time interval. And then on the y-axis, we have the rainfall intensity. And so you can see how this almost looks like a design storm. It's perfect. There's one hump. So this is like an ideal simplified situation. But now what we really care about is our total rainfall, because remember the goal is to get to estimate our Q, we need to know our total rainfall to then subtract rainfall that we lose, right? So in this step, we're still trying to get the total rain that fell within our watershed, let's say. And to get the actual rainfall that fell, we multiply our intensity times our
Duration.
times our duration. This A shifted, right? My A shifted. I think so. Need to put in.
You time interval by the rainfall intensity.
So A got shifted, right?
Yeah, I think it got shifted. Yeah, I got shifted. I'll explain it with this one better. So the area, we think about it, the rainfall under the area under the hyetograph represents the total rain that fell during that watershed. So if we wanted to get the amount of rain that fell during this second interval, we could multiply the interval times the rainfall intensity. Because at that point, we think about it, you're multiplying inches times hour. So hours cancel, and you're left with inches, which is the rainfall depth that fell during this 2-hour interval. That makes sense. And then we would do the same thing here. We would say this during this this interval. So 4 times my 0.4 is going to tell me how much rain fell during this interval. And I have this here. This one here shows that. So I have that 2 times this rainfall intensity would give me the rainfall that fell during this time interval. And so this is the area of this bar, and so on. And if I were to add all this rain that fell during these time intervals, I would get my total rainfall. So what that means that from the storm depth data that I had, the true amount of rain that fell was 5.14 inches. And so, but remember, not all of that rainfall turns into runoff. So this is kind of just like the first step to really determine our starting point of how much rain fell in the area. Does that make sense? And so that's a very simplified version. HMS can generate it for you. I know in school we kind of go through the calculations of it. But we do have softwares that help us work more efficient. So here we use I believe this was the 10-year rainfall data from the Williamson subdivision regulation manual. And this is like the mass curve that it generates for you. So HMS takes care of the interpolation because you see here how it only gives you the depth at 5 minutes, 15 minutes, 1 hour, 2 hours, 3 hours. But we care about, let's say we're looking at a 24-hour storm event, we need to know what happened in between. So HMS takes care of that interpolation instead of us having to do it manually.
I have a quick question for everyone. So when you look at the S curve, how would you, when you look at the curve, how would you relate the curve to because the curve is accumulated curve, right? So you're looking at the slope of the curve, you could tell how the rainfall, the hydrograph or the incremental, the hydrograph will be the incremental, yes, how the rainfall is distributed, or in what portion or what part of the storm that you would expect the heaviest rain.
In the middle of the storm,
Mm-hmm.
because it's like, that's when it starts like kicking
Yeah.
up.
Yeah, the slope is like almost like vertical, right? So you have very short period of time, you have a lot of rainfall amount. And then the beginning of the storm and the tail end of the storm, the slope is really low, right? That means that the change of rainfall over time is very little. So it's a flat. But then the center part of the halfway of the storm, you have a big drop or big precipitation. And
Okay,
right?
And we can see that here, how that steep slope is at hour 12. And then over here also hour 12 is kind of when we have the peak for our maximum incremental depth. And so when we think about uh, a watershed, what truly happens in a watershed, we have to think about water balance. So now that we have our precipitation, we have to also consider our rainfall losses, right? So not all that precipitation will turn into runoff. So then our next step is to really determine those rainfall losses. And there's different methods that are developed to account for that. So the most common methods that we see, but aren't the only ones, are the green amped method and the SES curve method. And when we think of rainfall losses, there's multiple ways that rainfall can be lost, like through infiltration, evaporation. But the main one that we focus on is infiltration. And each method here has its own way of estimating that rainfall loss. So from that total rainfall depth that we just calculated, we would subtract a calculated rainfall loss. Our first method here is the green and amp method. And the green and amp method is based on the soil type's initial moisture content, its saturated moisture content, its suction head, and its hydraulic conductivity. So the TxDOT manual does have these values listed. The only thing that you do have to do is determine the soil type that you have. And you can obtain that information from the USDA soil website. It's a pretty neat website. We can go in and like draw in your own area of interest, and it'll give you soil characteristics within that area. And based off that information, you could go to the text dot manual, for example, and see the specific coefficients that you should use for that type of soil.
Oh. So they even have the initial moisture content, like how would they, I guess, I know this is all modeling, but it's like if you'd had like a long drought, obviously the soil would have less moisture content, so like how do they estimate that, I guess? Like, I don't, maybe that's like far too in depth.
Ted, do you have?
I know, so that's a good question. So all these parameters that you have to input for the green and amp, so everything is, determined based on experiments. So they will have, let's say, this type of soil, and then they would pour the water over it. So then then they can quantify all these. Okay, so yes, so all this information will be when you start a project, then you will use the default values.
Okay.
And then, so a lot of times, this is called a calibration process. Let's say if you develop a model, um, and then you would run. This is also where the actual important. So we have design storm, and then the actual storm. So you would use the actual storm event as an input, and you run your model, and then you can compare it later on. You can, once the results, the obtained results, then you compare it with your gauge measurements. Okay, so then, because most of the stream in the county, they have gauging stations. So particular storm event, actual storm event, they will have records, so you can compare. Okay, so once you compare it and then you realize that your model is off, so there are several reasons it could happen. Let's say if you measure the record, the water surface elevation or the flow is a lot higher. So one of the contributor, the reasons could be, yeah, maybe your soil is fully saturated. Let's say if your event is like several days, so maybe the soil is fully saturated within the first few hours, first day, then that could be a reason, because once the soil is really cannot accommodate any more water, then everything will become your runoff, right? So that could be. So when we do things like this, then we can go back and see, or maybe we need to adjust your parameter to reflect that. Yeah, now soil is fully saturated. So modeling, let's say, iterative process. But all the information, the parameters that we have here, it's like a default parameters, so it should work for most conditions. Yeah, so unless you're seeing something that's really like very unique or extreme, then then you have to be.
Well, let me go back.
Yeah, but in general, these parameters are good for most conditions. Yeah. So should we?
That's what I was thinking. I was like, it's already 12.
Wow, it is. I thought it was like 10.
For lunchtime, yeah.
Yeah.
So we can resume maybe like, what time is it?
Well,
12.
Yeah, we can probably come back like around 1:05.
Okay.
Yeah.
Did you guys want to do lunch together or separate or maybe else plans?
We don't have any plan here, so it's up to you guys.
I was gonna run an errand. I need to.
Yeah. Then I guess we can do separately.
Sure.
Yeah.